I also forgot to press record. Oh well. Now I press record. So the pi CH2 is here, and then, I'm sorry, that's not, somebody should have said that's not the pi CH2. Don't let me do that, okay? What is that?
Sigma.
Sigma, okay. And then what did this part come from?
Sigma
CH3. So you've got, we're basically combining a pyramidal CH3 with a planar, or actually bent, maybe is the better way of saying that, a bent CH2. Okay, so this is just the minus combination, right? This is sigma CH3 minus sigma CH2. With the color change meaning a change in phase, there's a node in between both nuclei. You would describe these orbitals as both being majority bonding orbitals. There is a node here, but there's still a continuous wave function between CHs. And so we'd still call that a CH bonding orbital. We would not attempt to say which of the bonds this orbital refers to, because in molecular orbital theory, electrons that fill this orbital would simply be delocalized across the whole molecule. Okay? All right, so those are our two lower energy orbitals. They're at the bottom here because they come from all s orbitals, and s orbitals are lower in energy than p orbitals. All right, the next one, the gray sort of rectangle represents the node, the plane, which is the node, the spot where wave function goes to 0. And this gray node is in the plane of the page. What's the pink is in front, so this CH bond is coming out in front. What's that?
Yellow is in the back.
And yellow's in the back, yep. The wave function sign switches as you go from front to back. And this is then, what do you think this one comes from? On the CH2 side, what kind of orbital is that? Somebody said
Some kind of
pi.
Why is it pi?
Why is it pi? If you look, it comes from, you have a p orbital on that carbon, and then s orbitals. Oh, let's just fix that, shall we? P orbital on carbon and s orbitals on the hydrogens with in phase overlap. If we drew the spent CH2 from the side, it would look like this. And because you have sort of side-to-side overlap instead of end-on-end overlap, we call that a pi type orbital. All right, so now, go ahead.
So this is the case now we have.
Uh-huh. Yeah, so in front you have so you line up the pi CH3 with the pi CH2 in such a way that they line up side by side in phase. So just erased everything, but I'm going to color in. Man, all right. Let's see how to do this. Want to layer the colors appropriately. What a waste of time, right? So do you see where these come from? Any questions about where we got these? Now, if I'm, go ahead.
Why do they overlap like that? Why is it like pi and not something else? Why didn't they overlap in some other way?
Okay, what? Help me see what other way you're considering.
I just don't understand why we draw it like that. I don't know. Is it like the energy? Because of the energy, it's like.
It's okay. Go ahead.
I just don't know how to word it. I don't understand like these pictures. Just I can't like visualize that in my head. Like if it's pi, sigma, look at the pictures and.
Okay. Well, let's see. Are you okay with the concept of the group orbitals? Like, do you know what I'm talking about when I say pi CH3?
By bonds and like something like that. I'm not sure.
Okay. Right. So, who can help? What do I what do I mean when I call this group orbital over here a pi CH3 orbital? Go ahead.
You mean that it has one node, like a pi orbital, like a pi bond might when you were to if you were to draw this.
Okay.
And it's got the two bubbles on the sides. They don't directly overlap. They're kind of side overlapping.
Right. Good. So sigma and pi we're now using not to refer to an individual bond, but we're using it to describe the shape of an orbital. And the basic idea is this: for sigma type orbitals, the wave function is mostly along intermolecular axes. By that I mean the space between two nuclei. So, for example, do you see how in this sigma type pyramidal orbital, if I look at it and I put myself along the axis between any two of the atoms, the wave function is concentrated there. So this is sigma, and it would resemble a sigma bond. When you think of a sigma bond, you think of just a straight line between two nuclei, electrons held in between the two nuclei. So that's sigma we're using to describe more of a geometry or a symmetry than any particular bond. All right. Pi we're going to use for overlap of the wave function above and below the intermolecular axis, where on that axis, IA for intermolecular axis, there is a node where wave function equals 0. So the reason you can see with our conventional picture of a pi bond where you have two p orbitals on adjacent atoms that overlap with each other, and if you draw actually what the pi orbital looks like, you have one lobe here, one lobe there, and a node in the middle. That's overlap above and below the space between the two nuclei, if this were carbon here and this were carbon there. Along the place where you consider a conventional bond to be, there is no electron density, no orbital in the pi type orbital. Instead, it's above and below. Okay? So sigma type orbitals are, if they are bonding, they are going to have, they're not going to, bonding type sigma orbitals are going to have most of the time between nuclei along the intermolecular axis, there won't be a node. For pi type orbitals, there will be a node along the internuclear axis.
So these two like molecules are both pi CH3.
These are both pi CH3. They come from different things. We get them from different combinations. For example, the one on the right, if our coordinate system is x, y, and z, the one on the right we get by adding the 2px with 3 1s orbitals. And do you see how there's, if you put the hydrogen here, it's not like the hydrogen is overlapping directly with the p orbital, it's moved off to the side. And so that's a little bit more like a pi orbital than a sigma orbital. And if you, especially if you view these the way they actually look, if you do the calculations, you see definite pi type symmetry. In other words, there's a node here. And if I were thinking of bonding this to something else, shoot, I really did tell it not to go to sleep. I wonder what on earth is going on. So I'm just going to stand here, wiggling the mouse. Anyway, sorry. Now I can't get rid of the square of doom. There we go. If we, in particular, if we moved this group next to something else, it's going to overlap. Think of this spot, this carbon in the middle, as having an opportunity for something to bond to it. But if something came and bonded to it, this orbital is not going to overlap with it end on end. It's going to overlap with it in a side-by-side way. Yeah. All right, so when we bring the pi CH2 next to the pi CH3, I'm going to try to, well, you may think the coloring is a waste of time, and you may be right. And then I'll color the gray representing the node. And then the pink is going to be on top. Oops. Gosh. All right. And if we saw what this actually looked like, we would see, I'm just going to use a dotted yellow line here to represent the orbital that's behind the plane. And it's going to be this continuous lobe of orbital behind the plane of the page. And these two things are overlapping side by side in the same way that a pi bond would have two p orbitals overlapping side by side. And then of course in the front you've got this continuous lobe of electron density just opposite wave function sign. Okay? Okay, so that's the plus combination. If we take the other of our two pi orbitals, pi CH3 orbitals,
can I ask a question?
Yes, go ahead.
Do we have to know, like, why is it happening like that? Why are they overlapping like that? Or we just, like, we're supposed to know just, okay, this is pi CH3 and CH2, and we didn't, like, need to know, okay, like, why it's actually happening?
I think the reason why you probably already know. I mean, when you overlap orbitals together with the same wave function sign, you move lower in energy. So the why behind this is that if you bring these two pieces together they're lower in energy than they would have been separately.
Because let me that one on the top, it's also CH3 and CH2, but they overlap differently.
Right, and that's governed by symmetry. So what you have, the diagram is sort of difficult, so let me just try to circle things. This orbital here involves this pi CH3, and it can, if you think about what on the CH2 group it can overlap with, the only thing that works is this p orbital, because in order for orbitals to interact, they have to either line up end on end in sigma fashion or side by side. So that's why we choose this one as the partner for that one. Yeah?
So I'm looking at your organization of orbitals. Is the sigma out combination higher in energy than the pi CH3 plus p because of the increased number of nodes, even though the sigma out seems bigger, like it's got more space that it covers?
Right. So yeah, the question is, what do you make of this? Because this looks mostly like a carbon-carbon sigma bond, and this is starting to look like something like a pi bond. And wouldn't you expect this one to be lower in energy than that? I think when I drew this, I was following the results that come from the calculations. I would not necessarily expect you to predict that one would be versus the other. I think the conclusion, though, comes from the fact that the pi CH3 is lower in energy than the sigma out. So when we make a bond with this one, you would have to, and the thing it's bonding to is this non-bonding p orbital. So it seems reasonable that you wouldn't go quite as low here as you do for the pi orbital. All right. So when making molecules, you're looking for ways to bring the alphabet of group orbitals together, either end on end or side by side in a way that matches up. Okay, so the one that we just talked about, this overlap of the pi CH3 and the 2py orbital on carbon. This is sort of one of the aspects of hyperconjugation from valence bond theory. This tells you that some of the electrons, that this, you would say, the electrons that are associated here with carbon-hydrogen pi bonds, or sorry, carbon-hydrogen type bonding, are also a little bit on that positively charged carbon. Okay, so qualitatively, the picture I showed you here corresponds to what we say in hyperconjugation, where some of this electron density is actually over here. The orbital I just drew you maybe represents this, the hybrid structure between these two. And yeah, if you look at it, it looks like it's not so very much different from a pi bond, only you've got a methyl group over here instead of a CH2 group. It's mostly on the methyl group because the pi CH3 orbital is so much lower in energy than the pi CH than the non-bonding p orbital. All right. The other, the sigma out, I don't know that we'll spend any time talking about because that's exactly the same as we've done in previous situations. It looks very much like a sigma bond. I won't talk about the out of phase pi-pi combination, but I do want to talk about what the LUMO is. The LUMO is the combination of the p orbital here. Yes, go ahead.
The 2px of this pi CH3, is it behind the plane or on the top? Or
Where? Sorry.
this pi CH3, the 2px?
Here?
Yeah.
Okay.
Is it behind the plane, just like the way it is on the CH2? Are these two, are they the same? This two pi, yeah. Are they the same?
No. One, if
Because I'm looking at the results. The two yellow are overlapping.
yes.
So are they the same? How is it possible they are overlapping? I thought maybe the 2s is facing up, and then this other one is behind.
Oh, this one here?
Yeah.
Yeah, that is a representation of a p orbital on its side. It's not a particularly good one. It's hard to draw sort of a p orbital coming out behind the page and then coming out towards you. It might make more sense to draw it like this. Yeah, so this orbital comes from the 2py orbital on carbon with 1s orbitals on hydrogen. In contrast, this one comes from the 2px.
So they can combine the 2ps and the 2py.
These two don't combine with each other. These two are equal in energy orbitals that have different shapes, and you're going to make bonds with both of them.
And the result of the combination.
Right, so this one with the 2px in it can overlap with the 2px orbital on the bent CH2.
No, I'm talking about I thought it's also what formed this other side, the right. To the right, yeah. This one that you just yes, is it? I'm sure that's what is also formed from this combination.
Right, that is the one that we get from this one plus this one, yeah, to give us that one. And then up top is the out of phase combination of those two. Do you see? Oh, man. I really did change that last time, but I did it yesterday in group meeting and it must not have done what I thought it did. Right, so here is the plus combination, overlap of pi CH3 with a 2p, y, is it Y? Yeah. With a 2p orbital on carbon in phase, and then this is the out of phase combination. And this is the other one that is consistent with hyperconjugation from valence bond theory, because this tells us that the LUMO is not the place where the lack of electron density is not only on the positively charged carbon, but is also on the adjacent CH3 group protons, right? So when a nucleophile comes and attacks the LUMO, now you may have wondered before with like the SN1 versus the E1 reaction, why is it a choice and how do you know, and why are both options possible? And the answer simply is that the LUMO is on both places. So a nucleophile can choose to attack the LUMO here, or it can choose to attack the LUMO there. And depending on where it attacks, you have different consequences. If you attack here, you make a new bond between carbon and nucleophile. If you attack here, you make a new bond between the nucleophile and hydrogen, and then you make a new pi bond there. Okay? So as long as you're comfortable with the concept of hyperconjugation, you can use valence bond theory to get to the most important conclusions of molecular orbital theory. Okay. Now, that, you're not going to like this. That may not be the whole story. You've heard of carbocation rearrangement, right? That was when things went off the rails in I think, undergrad organic chemistry. At least when I first introduced that, they're like, come on, man. Things were complicated enough already. And I'm like, well, I didn't make reality, so sorry. But you've got these two ethyl cations here. And it's known that you can do what's called a 1,2 hydride shift, wherein this hydrogen with its electrons leans over and makes a new hydrogen-carbon bond with this second carbon to give you this second carbocation. Have you seen that before?
Yeah.
Understand carbocation rearrangement? Probably when you've been taught it before, it was taught to you in terms of equilibrium, that these are two, if we were to draw an energy diagram, these two carbocations are intermediates and there's some transition state in the middle. Presumably that transition state would look something like this. It would involve the hydrogen sort of being intermediate between the two, and you'd probably have some partial positive on all of those places. You would essentially have something shared between the two of them. And alternatively, you could say that this transition state is not an intermediate, is not a transition state, but rather is an intermediate. In other words, what if this is a 2-electron, 3-carbon bond? What if instead you have this minimum and then that minimum and then this minimum?
What's the difference between transition state
Right, great question. Who knows that? What's the difference between a transition state and an intermediate? Go ahead, Rachel. You want to take a guess?
It's
Yes?
like transition state, like it's like kind of when you have like resin structure, it's like a hybrid. It's like exists kind of like between it, but like wait, it was transition state and intermediate. But an intermediate is like a step that it has to go to before.
Okay.
it do the last one.
Right, intermediates occupy energy minima. That means at an energy minimum, motion of atoms in any direction leads to increase in energy. Right? At a transition state, motion in one direction and one direction only, well, forward and backwards, leads to a decrease in energy. But in every other direction, it's an increase in energy. So along a reaction coordinate, transition states are at maxima, and they represent, you can't isolate them, but they represent sort of the lowest energy pathway from one intermediate to another. Intermediates can be isolated and trapped and observed. Transition states can't be. You have to instead do other experiments to try to determine what you think the transition state is, and then you match those experiments up with computations.
Intermediates are lower in energy, right?
Yeah, intermediates are at energy minima. They occupy the valleys of a reaction energy surface. So what we're asking sort of is that intermediate, is that state where the hydrogen is sort of shared between two atoms, is that a transition state or is it an intermediate? Is it an energy high or an energy low? And it turns out that's kind of controversial. So let's look at the two options. Let's draw we've already drawn orbitals for the carbocation. Let's consider what the orbitals would be like for this structure, which we're not sure is whether it's an intermediate or a transition state. For the carbocation, we told you the LUMO looks something like this. It's basically a p orbital shared with the pi CH3 from the adjacent methyl group, and some of the LUMO is on those adjacent alpha hydrogens, or the adjacent hydrogens on the, I guess we'd call that the beta carbon, I don't know. Whereas the HOMO is shared between the two carbons and is mostly on the CH2 group, but with a little bit on the neighboring carbon. Now, if you shift the geometry just a little bit, imagine just taking this hydrogen and moving it over. If you move this hydrogen over here from the LUMO, it's going to occupy the node, right? So there won't be any orbital on it, and actually, the LUMO for this geometry is essentially the same as for a pi star. It looks like two p orbitals on adjacent atoms. And then the HOMO, if you move this hydrogen over, it doesn't change the overlap, and so this starts to look very much like a pi bond. Okay? So the question is this arrangement an intermediate or a transition state? And the answer is it depends, and it's complicated. Depending on what calculations you do, depending on what method and what basis set you use, some calculations will tell you this geometry is the minimum for the ethyl cation. Others will tell you this one. So what that likely means is there's not a huge difference in energy, and that the free energy surfaces for carbocations are often relatively flat, meaning it's easy to go from one carbocation to another, and the transition states aren't much higher than the intermediates. If you accept this as an intermediate, that's what we call a non-classical carbocation. This is a carbocation where you have two electrons shared between three atoms, and therefore the positive charge is distributed among all of those three atoms. You can think of a non-classical carbocation as being the hybrid structure for the following resonance structures. Isn't this fun, right? So you could imagine a resonance structure like this. And a resonance structure like this, and a resonance structure like this. Let's see. So we would see, and this is the essence of a non-classical carbocation. You have a sigma bond that's not even participating, and then you have 3 atoms that are sharing the same pi electrons, basically. Okay, the concept of a non-classical carbocation, that is a 3-electron, 2-center bonding, and one atom that's bonded to 2 things when it shouldn't be. See, this hydrogen's normally bonded to just one thing, but now it's interacting with 2. We call that a hypervalent atom. The concept of a non-classical carbocation has been controversial. We call these carbonium ions, and the reason they're controversial is because some people in the early days of physical organic chemistry did not really believe they were actually intermediates. And based on what we've talked about, you can see that the distinction is subtle. For example, we use the term carbenium to refer to a classical carbocation with a localized positive charge on one place. And we use carbonium to describe the either intermediate or transition state in which you have a hydrogen shared between 2 carbons with 2 electrons holding the 3 together. So the argument is really about, is the carbonium thing a transition state? Is it a high energy intermediate? Or is it actually the lowest the lower energy shape? Is it the one that's preferred over the carbenium options? Or are the carbenium options themselves transition states and the real intermediate is the bridged carbonium ion? And yeah, go ahead.
Don't double bonds have like a slight negative charge, or is that only in benzene?
Double bonds have a slight, what do you mean by
Like,
slight negative charge?
You know how on a benzene they have the positive on the top, the negative on the sides, and the positive on the bottom? And that's because there's a slight like negative patch on the double bond itself.
So I think what you may be referring to is something we're going to get to in a future chapter, but possibly you've been told, for example, that if you look at an electrostatic potential map, if we use red for plus and blue for minus, that the edges of a benzene ring are electron poor, whereas the faces are electron rich, right? That actually has to do, I mean, it does involve the pi electrons, but the simplest explanation for that is that sp2 carbons are more electronegative than hydrogens, and so you have all of these individual bond dipoles that make the protons electron poor and the carbons electron rich. But that gives you an electron rich face and electron poor sides. We'll talk about that more. In fact, we'll talk about it so much that you will hate it, but it's kind of a cool area of OCHEM.
I was just wondering, since you were talking about having that positively charged hydrogen associated with the bond, with that pi bond,
Yeah.
if that had any relation.
Yes, I suppose, in the sense that if you consider this resonance structure where you basically have the proton sitting down on top of a pi bond, you're attracting a proton to a pair of electrons. Yeah. Okay, and do you see how the distinction here is subtle? It's all a matter of what the relative energies are, and probably we're not dealing with very many kilocalories per mole between options. This brings us to a topic which we need to spend more time on, so I guess we'll do this next time, and then we'll move on to strain and other things in chapter 2. But that's the interesting thing you can do if you have a cyclopropane ring and an adjacent carbocation. This is another example of an option for a non-classical carbocation. And we'll it's in your text, you can look at it, it's in the notes, we'll talk about it. It has a great explanation in terms of orbitals, but I guess it's gonna take us a while to get there, so. I'm not concerned with getting through everything, we'll get what we get, and as I say to my kids, you get what you get and you don't throw a fit. So, and if we don't get to everything in chapter 2, I won't hold you responsible for the parts on the exam that are from chapter 2. We'll just play it a little loose, so. All right, thanks everybody, have a good weekend.